Professor Santanu Chowdhury, Professor Samir Brahmachari, Professor Partha Majumdar, and Professor Ashutosh Sharma, and others if they are there. First, I must thank Professor Santanu Chowdhury, or really compliment him, for organizing this excellent program on India's journey from aspirations to achievements in the scientific field. So I've chosen the title as From Raman Effect to Nuclear Power. And of course, it happens also to be the National Science Day. You know, we celebrate 4 days in science and technology. February 28th, the day the discovery of the Raman effect was announced by him, because Raman undoubtedly was the greatest experimental physicist India has produced. Mathematics Day, December 22, the birthday of Srinivasa Ramanujan. I'll mention him again. Ramanujan, the natural, magical genius, as he has been called. Engineers Day, September 20. Birthday of Mokshagundam Vishweswaraya, the greatest engineer, civil engineer India has produced. And Technology Day, May 11, the first day of the 1998 Pokhran test. Are you able to hear me clearly now? And see the slides? Hello? Santanuji? Hello? Are you able to see the slide and hear me?
Yes, we are able to see you, sir.
Oh, okay. Thank you, Sakshiji. Thank you. Now, we go ahead. See, when Raman got the Nobel Prize, and this is from a Vigyan Prasad Science portal, when the Nobel Award was announced, he says, I saw it as a personal triumph, an achievement for me and my collaborators. But when I sat in that crowded hall in Sweden and saw the sea of Western faces surrounding me, and I the only Indian in my turban and closed coat, it dawned on me that was really representing my people and my country. I truly felt humble when I received the prize from King Gustav. Then I turned around and saw the British Union Jack under which I had been sitting. And it was then that I realized that my poor country, India, did not even have a flag of her own. And it was this that triggered off my complete breakdown. I've seen Raman when I was a student in the Indian Institute of Science. He was a very strong person. And he's talking about his emotional breakdown. Today, 74 years after independence, the young people particularly, and also the older people, have huge opportunities to contribute to India's development in the future. You know, in this biography of Chandrasekhar written by Kameshwar Wali asked Chandrasekhar, how did India produce world-class scientists like Raman and Bose in 1920s? And Chandrasekhar's reply was, in the 20s, there was need for self-expression as a part of the national movement, to show the West that in their own realm, we were equal to them. Some of you might have seen this comment by Sommerfeld on Raman, that when he announced the discovery of the Raman effect, he said, Sommerfeld said, India had suddenly emerged in competitive research as an equal partner with her European and American sisters. Today, the motivation, particularly aspiration, particularly for the young people, it should be to make India a developed country in the fullest sense of the term, and also a knowledge economy. Developed country in the sense, in an economic sense, and knowledge economy in the sense of developing new knowledge and the ability to appropriate knowledge generated anywhere in the world. Bhabha, You know, Arthur Koestler talks of two kinds of leaders, the yogi and the commissar. Yogi is the contemplative thinker, and commissar is a man of action. Most of us are a mixture of part this and part that. When you look at Homi Jahangir Bhabha, you have unique mixture of both. At one time I was joking, he seems to be 100% yogi and 100% commissar, which of course arithmetically is absurd. See, many leaders, when they pass away, the whole system they have created collapses. Look at Bhabha, who died tragically in the air crash. Nothing happened really. Of course, we lost a great man who would have done much more for atomic energy, but he had created a leadership swarm around him. And so the atomic energy program continued to flourish. Bhabha was a renowned theoretical high energy physicist, pioneering work in Cambridge on electron positron scattering, now known as Bhabha scattering. But then the other side of Bhabha, that he led to the development of the nuclear energy program. He thought of building nuclear reactors indigenously at a time when we were not even building bicycles indigenously. Bhabha was universally respected around the world, founder member of the International Atomic Energy Agency, and he was the president of the first Geneva Conference on the peaceful uses of atomic energy in 1955. The great Srinivasa Ramanujam, this is from the biography of Ramanujam by K. Srinivasa Rao. For the earlier biography, The Man Who Knew Infinity. And you'll see that his famous notebooks, 100 notebooks, 4,000 theorems, and either they were very obvious to him, the proofs, or he didn't think it necessary, but he gave them without any proof. And as the Cambridge mathematician Professor Hardy says, wonder with awe and admiration that these notebooks, there were no mistakes at all. Now, the fact that he did not write down the proofs turned out to be a boon to generations of great mathematicians like George Andrews, who discovered one of the lost notebooks, and they could find problems. The theorem came from the Ramanujam's notebook, and they worked out the proof of that, and enormous amount of research was carried out on that basis. Of course, the new applications of Ramanujam's work go on in even cryptography and in coding theory, and I don't think he ever thought that these applications will emerge from his fundamental work in mathematics. As Nobel laureate Chandrasekhar says, as long as people do mathematics, the work of Ramanujam will continue to be appreciated. Next slide. Now we are, maybe I'll mention it again later, artificial intelligence and robotics is a part of intelligence. And there are some people who are scared, even Stephen Hawking was scared, that if they go on increasing the intelligence of the robots, then one day we may have super intelligent robots, AI systems which may take over the world. I don't agree. And I don't agree, but I agree with Roger Penrose, who says that no algorithm or cybernetic machine created by man can be smarter than man himself. Raman was this example. And the reviewer of the book, Ezekiel Rod from Hebrew University, says, no enhancement of human intelligence, this meaning artificial intelligence, opens a door to becoming a Ramanujam. And no algorithm is likely to produce robots with the abilities of Ramanujam. Coming to nuclear energy, of course, India has developed in so many fields, but I will spend some time on nuclear energy. And the Director General of IAEA, International Atomic Energy Agency, when he visited BARC, he said, I would like to conclude by noting that India's remarkable success in the field of peaceful nuclear technology is an inspiration for many developing countries. You know, we have a large number of reactors working now. And I've always said, if you have a complex system, technical system, safety and reliability go together. In your own car, if the brake and the clutch and the steering don't give you trouble, likely it is very safe. It will not get involved in any accident. Same thing for any complex system, including nuclear reactors. If they work for a long time without giving you problems, then they are very safe systems. See, on December 10, 2018, the indigenously built unit of Kaiga pressurized heavy water reactor in Karnataka broke the world record for continuous operation, 941 days, which was built, which was till then held by. Of course, they broke the record when they crossed 851 days. They said 852 days. Then they had to shut it down, 941 days. It was shut down. Okay, next slide. Because we are all worried about climate change. Everybody is worried about climate change, global warming, and carbon dioxide emission. Carbon dioxide is one of the greenhouse gases. Goes and settles upstairs, traps infrared radiation trying to get out of the earth. And this is what causes global warming. Already more than 1 degree warming has taken place. And everybody has agreed that we can't allow it to go more than 2 degrees. From 1 degree, 1 more degree is left. Actually, they say better to control it at 1.5 degrees. And this International Panel on Climate Change says key measures to achieve mitigation goals include development of renewable energy, nuclear, and carbon capture and storage. But for the next 20, 30 years, we are going to burn coal. And that's why when I was a PSA, we started this program on the advanced ultra supercritical thermal plant. But you raise the steam to 700 degrees centigrade plus. Then, for the same amount of carbon dioxide or the same amount of power that you produce, you emit less carbon dioxide. Of course, global warming in the short run has led, of course, the northern hemisphere, Norway and Sweden and Siberian people, they're very happy of global warming. But tropical countries are first affected, as you say, Stanford study, dragging down the economic growth in warm countries such as India and Nigeria. But in the long term, everybody is going to be affected. Next slide. This is India's in three-stage program set up during the plan produced during the time of Homi Bhabha and his colleagues. First, the heavy water reactors, as most of our reactors are, make plutonium out of uranium-238. Heavy water reactor, the isotope uranium-235 burns, undergoes fission. 238, which is most of it, 99% plus, part of it gets converted to plutonium. And plutonium is very good for fast breeders. It's called fast because it uses fast neutrons. Breeders, it's called because it produces more nuclear fuel than it consumes. And then you have got huge resource of thorium. Thorium will be kind of exposed to the neutrons, fast neutrons in these breeders, and will get converted to uranium-233, and hopefully in the long term, third stage, we will get into the plutonium, into the uranium-233, thorium-232 cycle. Of course, we can have additionalities of light water reactor. We don't have much experience in that except in our nuclear submarine. We are all, as I showed you, the slide which I showed you, the 3-stage, means closing the nuclear fuel cycle. Open cycle means you just take the spent fuel, throw it away as waste, which is absurd because it contains so much of valuable nuclear resource. So in this paper, which we wrote myself, Sinha and Patwardhan, 2007, we have shown that if you do that, at some stage, the total power that you can get from available global nuclear resources, fuel resources, will come down, and then it will go down. On the other hand, if you close the cycle through plutonium, uranium 233, then it becomes a sustainable mitigation technology. That's what India is planning to do. Next slide. And of course, we take care of the environment. As you can see here, the beautiful environment around one of our reactors. Next slide. Of course, all reactors are like that only. And these are the projects under construction. More have been sanctioned by the government. Next slide. And artificial intelligence based or machine learning based expert systems have been implemented in the Indian nuclear power plants, decision support system, system-based intervention guideline management system, and then false alarm suppression, prognostics of plant equipment, robotics. Robotics is a part of artificial intelligence for surveillance and safeguards. Because the final decision in any reactor is not allowed to be taken by a machine. That's taken by the operator of the nuclear power plant. But all this data becomes available to. Next slide. These are the new projects which have been sanctioned, 10 700 megawatt reactors, and also this Russian light water reactors. One day we hope we will also be able to indigenize this light water reactor technology like we did the CANDU type of reactors. 220 megawatt imported first by from Canada, and then now taken it up. We have taken it up to 700 megawatts, in between 540 megawatts. They are all totally indigenous design. Next slide. See, once I and the former Director General of IAEA, Mohammed Al Barade, were talking, and I told him that if you close the nuclear fuel cycle, as I explained to you, with plutonium, the same uranium will give you 50 times more power or even more. But if you close it using also thorium, go into the thorium uranium 233 cycle, we can draw perhaps 600 times more power from the same quantity of uranium. And that's the slide I showed you. So the use of closed nuclear fuel cycle with thorium 233 added. In fact, he asked me, can we then say nuclear energy then becomes renewable energy? I said, let us be a little modest. We'll say near renewable energy. Of course, there is also plenty of heavy hydrogen and also uranium in seawater. Next slide. These are, you see, nuclear is not just nuclear electricity and nuclear weapon. There is practically no field of activity, societal activity from which nuclear is absent. You can see here food preservation. We are able to kill the bacteria in this before packaging. Shelf life goes up. You package and then you expose it to radiation. Same thing with medical supplies. It can only limited to those which can be given this kind of treatment. So there's a Bhavatron for radiation treatment of cancer using gamma radiation. Water resources you can check using these techniques. I've also done under the Rotag in Uttarakhand. And so many other possibilities are there in gamma radiation for industrial safety and so on. Radiography, of course. Next. Today, advanced technologies are multidisciplinary. In fact, all disciplines are getting multidisciplinary. Physics, chemistry, and biology. Very difficult. Yeah. I think somebody else is trying to give a talk.
I think
Can, can you please mute other guys? Anyway, I was mentioning about physics, chemistry, and biology. Where is the boundary now? In fact, if you take density functional theory, as I may mention a little later, the theoretical chemists use it as much as theoretical condensed matter physicists. Look at the Nobel Prize for Venki Ramakrishnan. The Nobel Prize was in chemistry. The structure he solved was the ribosome, which is, of course, a biological material. Techniques is used are physical techniques. Same thing is true for technologies. To build a nuclear power plant or space launch vehicle or advanced fighter aircraft in mission-oriented agencies, they are not one technology. They are multidisciplinary. Disciplines are involved. And of course, they are all within an same institution. When I started this program on the advanced ultra supercritical thermal plant, then we had to bring in three organizations who could do that. They were BHEL, who are designers of power engineering equipment, NDPC, who are, of course, the utility, and it was a major materials problem. So we brought in IGCA, who are the experts in materials, because if they can do it fast beta reactors, there's no problem for them to do it for advanced ultra supercritical thermal plant. World over, giant science and technology projects also involve several countries, and India is in many of them as an equal partner. See, I remember when I was sharing the Board of Governors in 94, 95, I'm saying, the International Atomic Energy Agency, one Western member of the board, yes, not the board, but of the, among the, in the meeting, he said the developed countries are suffering from donor fatigue. That is when I developed this phrase, equal partner. I don't want any of you to, I want, will collaborate in science and technology project, but as an equal partner. Next slide. He's a very nice author. Here's Nassim Nicholas Taleb. Some of you might have read his book, The Black Swan. Black Swan is an unusual event because Black Swan, you expect the swan to be white. Black Swan means unusual event, but with serious consequences. Then he developed this phrase anti-fragile. You see, if something is robust, it will be resistant to shocks. No change. But if it is fragile, it will break down. But he coined the phrase anti-fragile as under stress, it will become better and better. And there are bacteria, for example, even probably COVID, so that it drug resistant bacteria, or even there is antibiotic talk about anti microbe antibiotic resistance. This is also, I have said, of a nuclear program. Of course, the technology denials in the earlier stages, we have resisted and overcome the shocks of that. I remember when I was director of BARC, I defined self-reliance not as trying to do everything yourself. Doesn't make any sense to me. It's a complex system all over the world. They buy subsystems from outside. But if anything is denied to you, including the proverbial wheel, you must have the capability to do it yourself. That's why I define self-reliance as immunity against technology denial. Today we are strong enough, we're very strong, getting stronger. We should learn to leverage international cooperation. We are doing it already to strengthen our own initiative. Like I'll see in the next. Before I go to that, let me make a brief mention of Pokhran. Pokhran was a totally indigenous effort because we had major support from one of the DRDO labs. Most of the work is BARC, Terminal Ballistics Research Lab. When we had to design explosive lenses, the initiative came from. But look at the physics of it. How many disciplines are involved? Shockwave physics, condensed matter physics, material science, nuclear neutron physics, radiation hydrodynamics, if you are building and radiation matter interaction physics, if you are building a thermonuclear device, and then advanced electronics and control systems and fabrication and processing technologies over a wide range. And that's why all this led us to an accurate prediction of the weapon yields. Because there were limitations when you, with the shaft that we had available, maximum we could test for 45 kilotons. But all the physics principles have been tested. That's why I wrote in this paper in 2008 that the carefully planned series of tests carried out by us gave us the capability to design confidently and build nuclear weapons up to 200 kilotons. Of course, a lot of work has been since done. Next slide. It is one diagram of sharing of nuclear weapons knowledge. And as everyone knows, there was sharing between US, UK, and France. France gave it to Israel probably to South Africa, Russia to China, China to Pakistan. But they all realized that India stands alone. That means we did no spying. And since all capabilities existed within our organization, there was no need to seek the help of anybody. Next slide, please. Of course, as I said, we are one. We go for international cooperation, equal partner basis. We have the Large Hadron Collider in Geneva, which we saw the Higgs boson. That all the, in this, what happens, protons are going around in 26-kilometer circumference circle. Two of them, two orbits, opposite direction. Once in a while, they are brought together. And when they brought together, energy disappears. And you have to read good old Einstein equation backwards. When mass disappears, you get energy. That's how we get nuclear energy, fission or fusion. But if energy disappears, you have to produce new particles. And they had to accelerate it to several tera electron volt before they got the Higgs boson. And we contributed all the sextupole, octupole, and decapole superconducting corrector magnets, 1,800 of them, to this orbit. The charged particle proton is bent by dipole magnets. Then it is corrected by these corrector magnets. And then as ITER, International Thermonuclear Experimental Reactor, our collaborator in the Indian side is the Institute of Plasma Research. Next slide. As you can see, one of the main things they are contributing is this largest cryostat built in the world, being built by L&T Hazira. The base has already been installed last year. I'm sure other things will happen very fast. Next slide. See, centers of nanoelectronics have come up, part of India's achievements. I remember a meeting which Arun Shauri was chairing. I said that we missed the microelectronics revolution. We shouldn't miss the nanoelectronics. Shauri, who spoke after me, said, if the PSI says we shouldn't miss, I'm asking him, what is he doing about it? So I told him, give me 100 crores. I'll fund two centers of excellence at the best possible places. That was Institute of Science and IIT Bombay, and they have become, as you can see, don't want to go into more details, how many papers have come, projects, and how much of international. Both of them are among the best centers of nanoelectronics in the world. Next. We also have the Indian National Network, which is connecting 1,600 knowledge institutions in the country. It's a research and education network, and it is already connected to the CERN grid, the European Union grid, the Internet 2 grid of the United States, and it's very good for collaboration, both national within the country and with outside international. Next one. Cyber security becomes the most important, one of the most important things today. The moment you have data moving from one place to another, it can be hacked. And they are also getting smarter, while the cyber defenders are getting smart. They are also learning to use AI and ML. And of course, we have many institutions working on this. The NTRO, National Technical Research Organization, SETS, under the PSA's office, and NTA, this National Critical Information Infrastructure Protection is part of MIC, designated National Nodal Agency. SETS is working in frontline fields. It's in Chennai, funded by the PSA's office. Blockchain, quantum cryptography, also post-quantum cryptography, and all these. And we have prepared a report. SETS has prepared a report under the chairmanship of Professor Ravindra Balaraman, IIT Madras, on what we should be doing on this artificial intelligence for cyber security, and also cyber security for artificial intelligence. Works both ways. Next slide. Data security, very important. I got this slide from a young mathematics professor in IIT Jodhpur, and he tells three ways. So I requested him for this slide. Encryption, we all know, but you can also do fingerprinting and watermarking. And all these are now possible for getting data security. Next slide. See, this is the chain. Research, development, delivery. Research, you create knowledge, develop it, and then you have to deliver it. You want to deliver it to industry, then the development phase has to be strengthened. In case of rural development, the delivery phase has to be strengthened. The academia industry interface, when you have to strengthen, it is specific to each technology. We had created, for example, the machine tools. And IIT Madras has created under Professor Ramesh Babu, Mechanical Engineering Department, has made the world's best grinding machine tool. And in rural technology, we have a number of programs under RUTAG, which is centered in 7 IITs, and is an open platform innovation strategy. It does both technology transfer, what Harvard Business School call knowledge brokering. What the Harvard Business School guys say, all innovations are new, old innovations packaged for a new environment. And we can do that for rural development and, of course, scaling of innovations. I've been very much interested in this because I've noted that for a person near the poverty line, her quality of life is a very non-linear function of her income. Whereas if you double my salary, my quality of life doesn't change. What changes possibly is my bank account. Next slide. India for dreams, coming to the end of my talk, is an India which is economically developed, where the human development index is high. An India which is scientifically advanced, with a knowledge economy, with the ability to generate new knowledge and appropriate knowledge generated anywhere in the world, and an excellent RDI ecosystem. excellence in basic research, including what I have called directed basic research, excellence in applied research, technology development, R&D-led innovation, and of course, all this has to be backed by high-quality manufacturing skills. We also want an India which is militarily strong. Of course, some sections I mentioned in India are already very highly developed, and we should have an appetite for risk taking. Phil Rosenweich, in his book This Idea is Brilliant, edited by John Brockman, says when it comes to technology breakthroughs or launching new products, better to act and feel than feel to act. If you are afraid of venturing into new technologies and want only proven technologies, and proven technologies I have said are a synonym for obsolete technologies, you will have to learn to take risks. And be the, if you want to be a leader, and that surely the young people want to be leaders. And Nobel laureate Abhijit Banerjee also says, poor people take up low risk, low return projects because they fear the risk. So they remain poor. The same thing is true for research. And last slide, to be present in the frontiers of science and technology, we need the term which I coined, coherent synergy in our SMT activities. Synergy is always there in our activities, but coherence involves, among other things, space-time relationship, space-time, develop it at the right time so that India gets maximum benefit out of it. Knowledge economy, which we all want India to be, needs both a technology superstructure. But you can't build the technology superstructure without the foundation of higher education and basic research. And should have, this is what I said before, India should have the ambition to be the first introducer of new technologies, advanced technologies. After, of course, due diligence, take care of their techno-economic viability, assurance about their safety, and so on. And let me worth repeating what I said before, the so-called proven technologies, unless subjected to continuous evolutionary improvements, are often a synonym for obsolete technologies. So I think I'll stop here. Thank you very much.